So you tried LHS minus RHS, and where did that take you with this one?
Didn't really take me anywhere.
Didn't take you anywhere. Okay, and this is the thing, and why they say algebraic inequalities is hard, right? Because it's not, there's not always like a foolproof way or a formulaic way of approaching it, right? There are some strategies, right? But like I said, when you start, it's not always clear how exactly it's going to work out. The more you do, though, the more familiar with these you'll be. So, like, hopefully that is one kind of saving grace aspect. What I say were the top two strategies when we looked at this. There was like 5. We're going to look through some of them today. Yep. So to put everything to one side is basically saying, okay, I have to show this. I haven't done that yet, so I can't work with the inequality in this way. It hasn't been proven yet. So what I have to do is I have to maybe look at LHS minus RHS. I'm putting everything to one side in some sense, right? So when you did that, you get something like this, a cubed. Well, that's better. Plus 1 minus, yeah, right? And then remember, after all this, the idea is that if I can show, actually, what was the condition I need to show for this one? Well, as in, what's the kind of end goal of this? Like, why am I put everything to one side? Why am I doing LHS minus RHS? Because remember, what's the thing I'm trying to prove, right? That this is bigger than this. And by taking LHS minus RHS, right, if I can show that that's bigger than 0, right, that's another way of doing that. Because it's not really obvious at the moment to see that, yeah, okay, cubic is a much higher power than a squared and a linear part. But, you have to conclusively show that, right? So kind of where do we go from here? Go back to your second condition. What was the second strategy that we were trying to do? Right, so the idea is that anytime you're trying this strategy, one of the key things you need to look for is that I have a square somewhere, right? Like I have something all squared, right? Because I know that has to be greater than or equal to 0. Would you guys agree? Yeah? So how can we do that? Well, right now it's not very clear, okay? But what you do notice is that we have 4 terms, okay? And you do notice we have a few a terms here. So what I'm thinking is, hey, is there anything in common I can factorize out? And I suppose here there's nothing if I look at it in this way, but if I rearrange it slightly differently, okay, maybe you can see what I can do. Because just don't forget about what the goal is. The goal is that I have, okay, I've got, sorry? Well, if you take out a, right? This doesn't really look like anything I can do. Right, nothing I can really do with it. It's not something I can factorize, not something I can really work with. So don't want to quite go down that route. But anytime we have 4 terms, back in like year 10, there was a method of factorization that you actually use. Think back to it. This is why you have to call upon all your different algebraic techniques. I was looking at it the other day actually, from some of my old stuff. If you have think about your non-monic factorization. How do you factorize non-monics? If you have 4 terms, there's a method of factorizing called grouping in pairs. I don't know if that sounds familiar. Sounds familiar. How does it work? It works by saying, okay, I've got 2 terms here. I've got 2 terms here. What's in common between? Okay, so well, this one we can take out a squared. And what I get left with the a minus 1. And then over here, I'll get left with, I can factorize out, take out minus 1, cool. And we get left with a minus 1. And what I'll get left with is this interesting expression. So I get a minus 1, I factorize that out, a squared minus 1. And this is where you have to go back to the original condition that you have. Hang on. Since a is greater than -1, this whole expression here, if I have something multiplied by something, okay, this has to be greater than 0 because my condition is that a is bigger than -1, right? And you try and substitute values into here, you'll see that that kind of works. They're both, if a is like less than 0 but bigger than -1, then these guys would both be negative and then they'd be positive.
We draw that graphic.
You could draw that graphic and do it as well. In the proof that I looked at, they had enough to say here that that's greater than 0 since a greater than -1, yeah. Maybe you'd have to explain that a little bit better.
Could you draw that? What would it look like?
It'd probably be, it's a cubic, right? So, so it's actually like a plus 1, a minus 1, difference of 2 squares. So it's a minus 1 all squared, actually.
Yeah,
So x at positive 1, negative 1, and maybe like that?
yeah.
Oh, yeah, okay, so then graphically, maybe you want to do that too.
And then say it's always positive.
Right, okay, cool. Yeah, that's a nice thing that I didn't actually pick up. Yeah, we can do this graphically as well. Yeah. Are you guys convinced that that's...
After drawing the graph?
Yes.
I'm pretty
Okay, yeah. So something I still have to look up is, yeah, what stage do we have to, how much do we have to explain? We don't want to get into essays and things like that, but we do want to.
At 1, there's touching 0.
Sorry?
At 1, it's touching 0.
At a equals to 1?
Yeah, look at the graph.
Huh. That's a good point, actually. Who wrote this one?
Yeah, it becomes 0.
Who wrote this example?